Good afternoon, Pre-Cal Honors Class students. So it's me again, Mr. Chen. So this one is the third part of the lesson for that chapter 1 and 2 of Pre-Cal Honors. So this one is just like a different structure to put in the transformation. So as you can see that, so we do have vertical translations up and down. So basically just change the y value and then translation with the horizontal phase shift. So just change the x value and then the vertical stretch factor, vertical compressions, and then negative with the x-axis reflections, and also the horizontal compressions with the coefficient in front of the variable. Well, this one is just another way to describe the transformation. Okay, so there's not more coming. So even functions, absolute value, reflections over that y-axis, all that. So in general, we just need to recognize the function with transformation as y equals a times f of b times the quantity of x minus h plus k. So a, if that's greater than 1, so that means it's considered a vertical stretch. Okay, so always like that. And then a is less than 1, greater than 0, then that means it's a vertical shrink or vertical compression. And then for the value of b also, so if b is greater than 1, so that means it's a horizontal compression. And then b is less than 1, greater than 0, then that'd be a horizontal stretch. And then the value of h, well, h is just the horizontal phase shift. And then k, which is the vertical translation. So that means moving the graph up and down. So besides all this, reflections, so you see the negative sign right in front of that whole function. That means it's reflected over the x-axis. If you see the negative right next to the variable, that means it's reflected over the y-axis. Okay, so normally that's what we use for Algebra 2, transformations with any kind of function. And then this one, in addition to all this, so we do have absolute value of f of x, so that means makes all the y value positive. And then f of absolute value of x, so that means an even function, for example, like the parabola. So if you're trying to make the parabola, so it's an even function. And then inverse, using that for inverse functions, so the line of symmetry is always y equals x for 13. So that means we just swap the variable. And then here's another one, it's called the reflection over line. So let's say we do have a general line of symmetry and you want to reflect through the line. So the way to come up with the transformation, it's always consider a, we don't change that, just keep the same position for a, the scalar or the scale factor. And then it's f of t times the quantity of x plus minus m over t. So this one, the quantity, it's pretty much the same as this part, but the only difference is that you want to take out the t as the greatest common factor. And then also right here for b, you want to separate it out. Okay, so for b, you want to separate it out. So basically this one, it's quite similar to the original form. It's like a reflection over the line. Okay, so this one is just another structure, another way to break it apart to find out the position. If you try to do it with transformation like this one, the mapping approach, that means this one would be considered like plotting points. So I do recommend you to do it in this way, in this kind of fashion, or just using that in general. So the value of a, b, h, and k. So now let's do some example. So instead of writing transformation with this type of structure, so I just want to describe what's happening with the transformation. So the transformation here is pretty obvious. So 2 units to the left, and then 2 units down. And then this one here reflected over the y-axis, and then it's 3 units down. And this one is just by the vertical vertical compression by the factor of 1/2. And then the 2 right here, you want to take out that 2 as well, because that 2, it's a scalar. So we got x minus 1/2. So vertical compressed by the factor of 1/2. And also this one, it's considered horizontal compress. Compression by the factor of 2. And then it's 1/2 unit to the right. And then the last part right here, so it's a vertical stretch by the factor of 2. And then it makes that as the absolute value, makes everything positive. So y must be greater than 0. And then the rest of this is quite similar. So describe the transformation. 1 unit shifted to the right. This one 4 unit up and then reflected over the x-axis. So sometimes this one can swap things around. Negative absolute value of x plus 4. And then this one, take out that 2. So we got x plus 2 quantity to the power of 3 minus 10. So this one is written as y equals 8. X plus 2 quantity to the power of 3 minus 10. So just consider a vertical stretch by the factor of 8. And then 2 units to the left, and then 10 units down. And then this part right here, by the vertical stretch factor of 2, so 3 units shifted to the right. So it's pretty obvious for some of the majority of this, and this one basically just follow through the translation, write a transformation, and graph each function. So this one translate f 2 units to the right, so x minus 2. And then sketch the graph. So 2 units to the right. So 4 minus 2 quantity squared, so 4. And then 0 minus 2 quantity squared, 4. So it's a parabola. And then this one similar, so vertically stretched by the factor of 3. So 3. And then to obtain h. Okay, so this one is called h of x. This one's supposed to call g of x then. So 3x squared, so 0, 0, the vertex. And then the next unit, 1 quantity squared, 1 times 3, 3. And this one 2, even function. So it's pretty straightforward. And here's the typical parent function that student need to recognize. Quadratic, parabola, cubic. So it's kind of like a dancing arm. And then absolute value, v shape. Radicals of x. It's a half sideways parabola, cube root of x. It's a sideways cubic curve, or it's like a snake. And then y equals x, the line of symmetry for the inverse function. Rational function, the normal one, we do have 1 over x. The va, the y-axis. ha, the x-axis. So this one's supposed to be dotted. It shows that the boundary for the curve. Exponential functions, the value of k, if that doesn't appear, it's always considered 0. And then natural log of x. Sine curve, roller coaster, cosine of x, bell curve. And then tangent, it's just like a cubic curve bounded with the asymptotes, negative pi over 2, pi over 2. And also it's very important for you to recognize the structure of this type of functions with the transformational form. So this one normally is written as a times x minus h quantity squared plus k. So y equals a times x minus h quantity to the power of 3 plus k. And this one is y equals a times absolute value of x minus h plus k. And then the rest of this, they're quite similar. So y equals a square root of x minus h plus k. Now you might be wondering, what about for b? Another scale factor right next to the variable. Again, the value of b, sometimes you can factor that out. You can take out that as part of the scalar and then multiply that with the coefficients, so that becomes the value of a. And then this one says y equals a cube root of x minus h plus k. And this one is just like the slope-intercept form. Y equals ax. A times x minus h plus k. And then for the rest of this, similar. So it's y equals a over x minus h plus k. Exponential functions, y equals a times e to the power of x minus h plus k. Natural log, similar, a times natural log of x minus h plus k. And then what about for the trigonometric functions, the ultimate form? So y equals capital A, the amplitude, sine of the scalar b times the quantity of x minus h plus k. And then for the cosine curve, similar, a cosine of b times the quantity of x minus h plus k. And then tangent, without the amplitude, the scalar a, the vertical stretch factor, or vertical compression factor, so a times tangent of b times the quantity of x minus h plus k. And also don't forget about the one cycle test for this one. It's always from 0 to 2 pi. One cycle test for this one, 0 to 2 pi. And then one cycle for tangent, negative pi over 2 to pi over 2, because of the parent graph. And now to look at that one of the problem here, given that f of x, we don't know exactly what that is, but this one it goes all the way from 0 to 4. And on the same graph, sketch the following transformation and state the domain of the range. Describe each transformation. Well, let's describe the transformation. So it's one unit shifted to the left, and then by the scalar, the vertical compression factor, 1/2. Okay, so vertical compress by 1/2. So it's one unit shifted to the left, and it's one unit up. So it started with a point, so you probably want to use that, the xy table. So it started with 0. So 0 plus 1, then that'd be 1. And then f of 1 right here, that's 2. So this one turns out to be 2. 2 times 1/2, which is 1. And then 1 plus 1. So 1 plus 1, which is 2. So this one is actually being shifted all the way up here. Started at 0. So I probably want to set up the xy table. So x, and then put into the factor x plus 1. So one thing at a time, and then f of x plus 1. And then the other column, 1/2 times that f of x plus 1. And then finally, just f1 with the final results. So what we got here started with 0 for the x value, so 0 plus 1, which is 1. And then f of 1 right here, well, f of 1, which is considered 2. But 2 times 1/2, then that'd be 1. And then 1 plus 1, then that'd be 2. So 0, 2. And then for the rest of the positions, the turning point, you want to do the same thing. At 1 here. So what happened at 1? So at 1, we do have 1 plus 1, then that'd be 2. So what's f of 2? So f of 2 originally, what is that? It's about 2.5. And then 2.5 times 1/2. So 0.5 times 2.5, which is, okay, so decimal times decimal, 25 to 125, 1.25. And then 1.25 plus 1, 2.25. So at 1, so we got 2.25 with the new position. Okay. And then the next position, we do have 3 or 2. Okay, so use 2. So basically just plug in those integer and find out exactly. And this one is the line segment, so instead of using that 2 right here, we can use 3, because again, the turning point. So at 3, so always pick the position with the turning point. So 3 plus 1, then that's 4. And then f of 4 right here, that's 3. So 3 times 1/2, 3/2, 1.5, plus 1, 2.5. So the new position at 3 is 2.5. So 3, 2.5. And then what about the final positions? F4. If this one's a constant, so eventually this one should be constant as well. So let's check that, F4. So 4 plus 1 is 5. This one, there's nothing we can evaluate. But one thing we can do, it's constant, so we just need to connect it. So it's going to be like this. Okay. So it shows that the new function after transformation. And then the other one, this one shows that the 2 right here, which is considered horizontal compression. So horizontally compressed by the factor of 2. And then negative reflected over the x-axis. Okay, so one thing at a time. So again, so set up that kind of like an XY table, x, and then you want to find out 2x, and then f of 2x, and then after that, negative f of 2x. So with the exact same function with the original position, so started with 0, so 2 times 0, 0, f of 0, that's 0, negative, well, there's no such thing, negative 0, so just 0, so it remains at the exact same position. Because there's no vertical translation for this one, so nothing's moving here. And then the next one, you want to choose 1, again, the turning point. 1, so 2 times 1, 2. And then f of 2, so f of 2 originally, so that would be what, 2.5. So negative 2.5 reflected over the x-axis, so negative 2.5, somewhere down here. Oh, that's right at 1. 1 comma negative 2.5. So it's right here. Okay, so the next one you want to find out. So again, turning point. So we got 1. I mean, you can pick 2, but 2, this one's connected all together. So another turning point, then that'd be what? 3. So let's find out what happened at 3. So 2 times 3, 6. So f of 6. Well, we don't know what that is. Doesn't show anything here. Okay, so this one, nothing we can figure it out if we try to plug in those points. So instead of using 3, then let's try 2 once again, and then we'll just find out the pattern here. Okay, so let's just connect this part. So it's horizontally compressed. Okay, so if that's compressed, so that means this one's going to be considered declining slowly. But let's find out, so at 2. Just using that table. So at 2, so we do have 2 times 2, 4, f of 4. Originally, f of 4, that's considered 3. So negative 3. So 2 comma negative 3. So again, this one is just compressed. Horizontally. And then the rest of this. So you just want to try 3. That one doesn't work because we don't know that f of 6. It doesn't tell you that. So again, this one, consider that compressing slowly. So extend it all the way to here. And then this part right here should be flat. Okay, so just follow through the pattern, reflection. Okay, so now let's see what else that we have for another one. So this one describes the transformation comparing that. So this one basically showing it's 1/8, so vertically compressed by the factor of 1/8. And then it's horizontally compressed by the factor of 3. But for the 3 right here, you want to take out that 3. So it's y equals 1/8 times square root of 3 times the quantity of x plus 2. So the value of A, it's 1/8. B is 3. And then H is negative 2. Okay, so normally once you sketch the graph, so you started off with the vertex, so h comma k, negative 2 comma 0. And then in order to get the point for the rest of this, we can always set up some position. So in order to make this one as a perfect square number, so let's try negative 2. Well, that's already given. Let's try something else. In order to make this one as 9, so let's say we're using 1. So 1 plus 2, 3. 3 times 3, 9. Square root of 9, 3. 3 times 1, 8. 3 over 8. So at 1, it's 3 over 8. Okay. And then what else that we can apply? So try to make this one as a perfect square number. What about 4? 4 plus 2, 6. 6 times 3. Then that would be 18. So that would be too big. So just try something else. But once you connect it, this one is just like, it's a half sideway parabola. Compared to the original one started at 0, 0. And then at 4, then that would be 2. So obviously showing that it's horizontally compressed. And then the rest of this, they're pretty similar. So identifying the transformations and follow through the guideline. Translate 1 unit up, compress horizontally by the factor of 1/8, vertical stretch by the factor of 3. And also the rest of this, pretty similar. Like this one here, you probably want to sketch the graph first to find out the new equation. Okay? So like this one, you want to sketch the graph for that function. Quadratic, so minus 1, 1 unit to the right, 1 unit up, so it's 1, 1. And then y equals negative 2. That's just the line of reflection. It's reflected over the line of symmetry here. So this one, compare that, is 3 units away for the distance. So that means the position here should be 3 units away. So negative 2 minus 3, then that would be negative 5. So for the new vertex, this one should be 1, comma, negative 5. And then we're using the exact same scalar. Okay, so for the vertex, then that would be considered y equals, for the brand new function, x minus 1, quantity square, plus 5. Just like that. So once you sketch the graph, you'll see that the difference, the distance right in between. It's always the equal distance. And this one is similar, but there's a formula for that. It's reflected over the line of x equals 0. That means it's the y-axis. So if that's reflected over the y-axis, so it's y equals 3 times square root of negative times 1 minus x. Like that. In other words, this one is just considered y equals 3 times x minus 1. So given the graph of f of x, sketch the transformations 1 over f of x on the same Cartesian plane. Well, this one is just y equals x. And then this one's kind of like the reciprocals. Reciprocals, that means, well, whatever that we have the y value, we want to divide it. So let's say, again, it's the xy table. So let's say that you started with 0. So f of 0 here is 0, but there's no such thing 1 over 0. Then that would be undefined. Undefined at 0, that means over here it's a VA. And then the other one, you want to plug in 1. So f of 1 originally, that's 1. So y equals 1. Same position. And then what about 2? So f of 2, then that's 2. But here's what turns out to be 1/2, the reciprocal form. So 1/2. And then the rest of that, 3, 3, 1/3, so on and so forth. So this one's getting smaller and smaller and smaller. Okay, so eventually the graph is kind of like this. Kind of like a decay. Exponential decay. So once you connect them all. And then the other part of the graph is going to be like this. So this one is one of the interesting ones. So try to follow through it so it's like a rational function. So combination functions. So this one is basically using that function operations. Combine the number, subtracting the number. So like this one, f of x, so f of negative 2. So the parabola, then that's what? The up parabola, this one is f. The upside down parabola, that's g. So f of negative 2. Okay, so which is what? 4. And then g of negative 2, 0. Okay, and then combine them, just 4. Similar with the rest of this. And then this one here, similar. So g of negative 1. So g, which is this cubic curve. So g of negative 1, which is 2. And then f of negative 1 down here, which is negative 2. So 2 minus negative 2, then that'll be 4. Just like that. Find the domain of each function. Again, it's all about the restrictions. So set that denominator equals 0. So x equals what? Negative 1/2. So it's negative infinity to negative 1/2. Union, negative 1/2 to infinity. Well, how do I know this one's so fast? Because that it's rational functions. So the only restriction applying, it's just the denominator. It cannot be 0. And then radical functions, it's all about the parent functions. It's a half sideways parabola, 2 unit down. Okay, so that means x must be greater than 0. And then this one here, pretty much x can be anything except 0. So negative infinity to 0, union 0 to infinity. And basically this one can be any number, all real number. And the rest of this is all about using compositions to find out, simplify each expression and give their domain. Use the function from problem 2. So find out the brand new function and then find out the domain. Compositioning, so one function in terms of the other. Okay. So this one composition, m of x. So started off with radicals, so square root of x minus 2. And then put it into the radical, so 1 over 2 times this whole quantity, square root of x minus 2, and then plus 1. And you want to simplify it a little bit more, so it's 1 over 2 root x minus 4 plus 1, so it's minus 3. And then this one is right in the denominator. Normally the radical cannot be less than 0. So this one also cannot be 0 as well. So that means 2 root x minus 3 must be greater than, it must be greater than 0. And then from there you want to solve for x. Again, it's non-linear. Well, let's see. So we do have two conditions here. So 2 root x must be greater than or equal 0. But also, you need to find out the restriction for this part. So set this one equals 0 first. So find out that the possible 0. And also do the sign test, because that's the nonlinear. So I would say that it's greater than 0. And then solve for x. Okay, so the rest of this is quite similar. So using the function from example 4, find the value. Okay, so basically that's just compositions. This one's just a product, function operation. So this one can be split into f of 6 times g of 6. And this one started with g of negative 3.5. Okay, so g of negative 3.5. So negative 3.5 plus 3, which is what? Negative 0.5, quantity square. Then that would be 0.25. Okay, so g of x plus 3, quantity square. So negative 0.5, quantity square, 0.25. And then plug in 0.25 into the quadratic. So it's 1 over 0.25, quantity square, minus 4 times 0.25. We're using that as a fraction, so 1 over 1/4, quantity square, minus 4 times 1/4. So 1 over the quantity of 1 over 16 minus 1. This one subtracts, so it's negative 15 over 16. Take the reciprocal, so negative 16 over 15. And then the rest of this, they're quite similar, so try to finish that with the practice. Composition, so you want to evaluate what this is. So it looks like this one is the inverse of the other functions. So once you put it into the composition, eventually the expression is going to be x. So one of the interesting facts is that if you do know that f of x and g of x, and they're considered inverses, okay? So they're considered inverses. So anytime they do like the compositions f of g of x or g of f of x, and guess what? The final result is always x. Okay, so check that. So that's the special properties for the inverses function. So this one is linking to the inverse functions. The way to find the inverse, there's always a line of symmetry. So y equals x. So give some points on the line of f of x equals square root of x minus 1. Okay, right here. And then the inverse, you just need to swap the xy value. So just swap them. So if that's 1 comma 0, so that means turns out to be 0 comma 1. And let's say this point here, it's 1 comma 1. Okay, so 1 comma 1, it's also what? Once you swap them, it's also 1 comma 1. No, 2 comma 1, then that'll be considered 1 comma 2. 1 comma 2. Okay, like that. So if this one is going this way, so that means the other one is going to be kind of like a parabola. Okay, so once you connect them, symmetrical with respect to the line of symmetry. So f of 2 equals 1/5. What's the inverse of 1/5? Well, that's just 2. Swap the xy value. So inverse of y equals x cubed plus 1, show that it's 1 to 1. Okay, so x cubed plus 1, so sketch the graph. So cubic functions, 1 unit up. Okay, so what happens if I plug in 2, 8, 9, but that's going to be out of bounds, so let's plug in 1. So 1 plus 1, 2. Negative 1, 0. So it's going to be like this for the original function. Is this considered 1 to 1? Well, 1 to 1, that means you want to do the horizontal line test. So what that means, if you find out the line touches the graph at one point, only intersects the graph at one point, then it is 1 to 1. So it's about the horizontal line test. Okay? And then verify the inverse algebraically. Okay, so find the inverse, swap the variable. So x minus 1, x cubed, and then cube root both sides. Rewrite that inverse f of x. So this one is something that we talked about in Algebra 2 already. So nothing special. So cube root 1 unit to the right, and then it's going to be like this. And then the rest of this is quite similar. So find out that the inverse functions. So state the domain. And then find out the restriction if necessary. So let's do this one. So y equals x equals y minus 1 over y. And then this one here multiplied by y on each term. So we got yx equals y squared minus 1. Bring all the y terms together after we swap the variable. So we multiply by y and then bring them all together because this one is quadratic. So it's 1 equals y squared minus yx. And this one looks like it's non-factorable. So if that's non-factorable, so we need to complete the square for this. So complete the square, 1 over 2. So y squared minus yx plus 1/4. Because that b is 1. Okay, so, and also with the variable x, so probably consider adding x squared on both sides. So this one is one of the interesting one. Yeah, adding 1/4 x squared. And then by the time that you factor this, so this side here, you want to add 1/4 x squared. So try to factor this completely. So it's y minus 1/2 x quantity square. And then we got 1 plus 1/4 x squared on the left hand side. So this one, take the square root, because you want to isolate that y by itself. So it's y minus 1/2 x, and then square root of 1 plus 1/4 x squared. And then add 1/2 x on the other side. So then that'll be the inverse. It's quite interesting. Okay, so this one also finding the inverse, swap the variable, and then solve for y in terms of x. The hint for doing that, after you swap the variable, try to cross multiply. And this one, let f of x equals a times this quadratic cubic function. Find a if inverse of 9 equals 2. So what this means is that after you swap the variable, so inverse of 9 equals 2, so that means back to the original function, it's like 2 comma 9. So the value of x is 2, and then y is 9. So 9, and then 8, so 2 times 2 cubed, plus 3 times 2, plus 5. And then from there, you want to solve for a. And then the rest of this is just like review things that we've been covering so far for this 2 unit. So again, the majority of this is from Unit 1, Chapter 1, and part of it from Unit 2. And the other packet I'm going to send out next week. So the first part of it, it's also considered Unit 2. So we're going to continue with that Unit 2 next week. Okay, so thank you for watching the video. So any questions that you have, so please let me know. And I'll see you guys next time. So you guys have a great one.